In this video, we will go over how to do a proof by contraposition. Okay, so this is our second proof technique that we will talk about in our class. All right, so recall that when we have an implication, if P then Q, that's equivalent to its contrapositive. And the contrapositive says, if not Q, then not P. So those are equivalent. And sometimes it's easier to prove something by showing the contrapositive is true, instead of showing that the initial thing is true directly. So our method for showing this new implication, the contrapositive, will be assume not Q, that's the new given, that's true. That's another way of saying, well, if not Q is true, that means that Q is false. We'll assume Q is false. And then we want to show that that not P is true. And that's another way of saying that P is false. So we're going to assume that Q is false and try to show that that means P is false. And that will prove the contrapositive, which is the same thing as proving the original, because they're equivalent. All right, so let's look at an example. For all integers a and b, if a times b is even, then a is even or b is even. So if I multiply two integers and it's even, then either the first one is even or the second one is even. So maybe kind of conceptually, from what we know about evens and odds, this should be true. Okay, so let's try to prove this. First, I'm going to try a direct proof and see where this kind of breaks down. And let's think about our scratch work. So for my scratch work, what is it that we're given, / we know, / we get to assume is true? Well, the a and the b are integers. We know that. So we know a and b are integers. And then we have this if-then statement. And an if-then statement, the if part, we get to assume is true. So I'll put a bullet point next to that. That means AB is even. And what I want to show is the then part, which is bullet point here. A is even. I either want to show A is even or that B is even. Okay. So, let's do some more scratch work thinking. If AB is even, that means that AB is equal to 2 times some integer k. AB has the form 2 times k. And eventually I'm trying to get a connection between this given stuff with what it is that I want to show over here. Because to show that A is even or that B is even, I would need to either show that A equals 2 times some integer, or that B is 2 times an integer. I would need, let me just write that below, 2 times blank parentheses, where this is an integer. Okay, not totally sure at this point if I can take my A times B, and which equals 2k, and get it into a form where I have A is 2 times an integer, or maybe B is 2 times an integer. But maybe at this point, let's kind of try seeing if I could just dive into the direct proof at this point. Even though I don't see a connection right away, what if I just try diving into the direct proof? Okay, so in the direct proof, we start off by writing what it is that is given, / we get to assume is true. So I'm going to let A and B be integers, so they are an element of Z, such that, I'll write S dot T dot to abbreviate such that AB is even. So we start off with what is given / what do I get to assume is true. Then we break this down and say what this means according to our definitions. So this means there exists a k, which is an element of Z, so an integer, such that A times B equals 2k. A times B equals 2k. So that's the definition of what it means for AB to be even. And now I'm going to do my manipulations. I have an equation for AB, but I'd like to either isolate A or isolate B. So maybe I'll try dividing by one of these variables. So, then maybe if I divide both sides by B, I would get A equals 2k over B, Well, there's one possible problem if I divide by b, which is what if the b was 0? There's nowhere in the problem so far where it says b is non-zero. That's maybe a problem. Let's say I ignore that for the time being. So I have a equals this thing. I'm hoping that that's 2 times an integer. And I do see a 2 here, which is promising. So I get this equals 2, and I can write that as 2 times the fraction k over b. And I really need this k over b to be an integer. What I know is k is an integer. I know b is an integer, but I don't know for sure that when I divide 2 integers, it's necessarily an integer. Oh, so I'm running into a bit of a dead end here. So we are not sure if this is an integer. So I'm going to put a sad face here. We're kind of getting stuck trying our direct proof. So that's one of the reasons we might try to prove something using the contrapositive, doing a proof by contraposition. Because we tried direct proof, but it's just not helpful. That will happen often in proof statements where doing a direct proof just isn't helpful. But luckily, we have other methods like the contrapositive. So the contrapositive of this statement would be, we'd try to prove if it's not the case that A is even or B is even, then it's not the case that AB is even. Okay, so let's break this down. So if I'm negating an OR statement, I can use my De Morgan's laws, right? Which says, so I have my if right here. The De Morgan's law says, well, the OR will change to an AND. It'll change to an AND. So if it's not the case that A is even or B is even, that means A is going to be odd and B is going to be odd. So we negate both of these and the OR changes to an AND. So if A is odd and B is odd, then I'm going to negate AB is even. So then AB is odd. AB is odd. So that, I'm going to put this in a little thought bubble, that is my contrapositive. This is what we are going to try to show at this point. So what I want to do at this point is I want to have you pause the video and try, based on what this new if-then statement is, to see if you can do the scratch work and get this proof started. It takes a lot of time and practice to do proofs. So you really there's just no way around this than to really practice it yourself. Watching other people like me in these videos do proofs, that can definitely be helpful. But there's no replacement for actually trying it yourself and seeing, can I actually do this thing on my own and practicing it? So pause the video for about 4 minutes to try this. Pause it in 4, 3, 2, 1, and try this. All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it. Okay, so what is it that we are given, that we get to work with? Well, we have the if part of the statement. That's what we get to assume is true. So I'll put a bullet point here. So we know, we get to assume that A is, let me just write it more shortly. A is odd and that B is odd. We get to assume that's true. And I want to show the then part. I want to show that AB is odd. So let's break this down a little bit more. If A is odd and B is odd, well, that means that A will be equal to 2k plus 1, where k is some integer. And same thing for B. B will be equal to 2 times, I don't want to use the same variable, because then I would be assuming it's the same for both A and B, which is not necessarily true. Maybe I'll call it, let's say L, 2 times L plus 1. Okay, and my ultimate goal is to show A times B is odd, so I'm going to need to multiply the A and the B, and hopefully get that this equals 2 times some integer plus 1. Okay, this looks more promising, because I have an A, I have a B. I think I'm going to multiply them together, and hopefully when I do that, it will have this form. So I think I have an idea for how the no column and the want to show column can connect. So I'm going to start to tackle the proof. Okay, so I start off the proof by writing what it is that I know / get to assume is true. So for this problem, I get to let A... let me say one thing first. I'm going to indicate that I'm doing the proof by contraposition. So let's proceed by contraposition. Anytime I'm not doing a direct proof, it's helpful to indicate what technique we're using. So let's proceed by contraposition. And when we do that, we get to assume the negation of Q, the negation of our conclusion. So we get to assume that A and B are odd. We get to assume that A and B are odd. Okay, so that's what I get to assume is true. Those are my new givens. Then we break down what that means using the definition of odd. So this means there exist, and because I'm going to use a K and an L in this case based on what I did in my scratch work, let's just try to do that at the same time. There exists K and L, which are integers, they're elements of Z, such that A equals 2K plus 1 and B equals 2L plus 1. So we've broken down what it means for A and B to be odd using the definition of odd. Now I think we're ready to do our manipulations. And we said we think what we need to do is multiply the A and the B together because we're trying to prove something about A times B. Okay, so if I look at A times B, A is 2K plus 1. Multiply that by B, which is 2L plus 1. And okay, we can expand this. We could distribute it out to get 2KL. We'll get plus 2K plus 2L and then plus 1. We're really hoping to show that this ends up being 2 times some integer plus 1. And I can do that by factoring a 2 out of these 3 terms. So that gives me 2 factored out times KL plus K plus L. And then we have that plus 1 outside of everything. Okay, and I know this is an integer because we said K and L are integers. And if you multiply and add integers together, that's an integer. So I'm going to assign a new variable to represent this whole thing in the parentheses. So I'm going to let KL plus K plus L be equal to, maybe I'll call that M. And that is an integer. That is an integer. Okay. This means that our A times B that we started our manipulations off with was equal to this at the end, which just equals 2 times M plus 1, where the M is an integer. But that's precisely what it means for this thing to be odd. It's 2 times an integer plus 1. So we have reached our conclusion. So I could say thus, A times B is indeed odd, like we wanted to show. So we've reached our conclusion. We've reached what we wanted to show. So I'll write my symbol for done with proof, which is my square, and it's shaded in.